by multiple stage events is just more than one thing happening at the same time. So the first activity we're going to look at today is where you're rolling 2 dice, so more than one. Rolling 2 die at the same time, and when we roll 2 die at the same time, then that's called a 2-stage event. And we're going to look at probabilities associated with the 2-stage event. And like I said, we're going to start with this little activity before we start determining probabilities. I'll let you read the preamble to the activity whilst I set this up. So we have a scenario here where we're calling this a horse race. And the horse race is where we roll 2 die, and each number that comes up, the sum of the numbers that come up, is represented by the roll. And so what I want you to do first, before we do anything else, is I want you to predict which horse you think's going to win. You've got horse numbers 1 all the way up to 12. The numbers that come up will be based on the sum of the 2 die that we roll. I want you to write down just on the side, there might be a prize for the best predictors, what number you think's going to win. So just write it on the side here somewhere. And then we'll see what happens. Now the first 6 die, the first 6 throws or first 6 events have occurred. We've got 1 and 2's come up, so that's a total of 3. So we just shade that. So I'm just showing you how to shade this now. So we're going to do the first 6 together. 6 and 3 have come up. So that's 9. 6 and 5 has come up. 4 and 3. 4 and 5. 1 and 5. So total, they're your totals of the 2 die, and that's so far. And so the aim of the activity is for us, the horse that gets to the end, to the finish line, after all these multiple 2 die rolls, is going to be the winner. So that's the one I wanted you to predict here. So if you want to change your prediction, now we've done that, this is the time. You get one chance to change your prediction. So you want to change it to 9? By all means, go ahead. All right, so now I'm relying on you because I've got to set up the 2 die here. So here are the 2 die. And we're going to start. Okay, here we go. Oh, are you serious? Well, that's not going to work. Let's see if I can do another one. Let's try this one. Oh my gosh, this is so slow. Okay, here we go. 5. 1 and 4 makes 5. This is graphing it for me, so even better. Yeah, so shade. Do your shading, right? Keep go. 3. Right, I'm going to do this a bit quicker now. Come on, otherwise it's going to get boring. Keep going. 9. 11. Oh my gosh, it's reset, sorry. 12, that was 2, I guess. 12. 6, let me know when something, so you hit the target at the end. 8. 11. 3. 6. 3. 10. 3. Anyone pick 3? 3's doing all right. 5. And 2, 3, 4 and 5 didn't even get a mention. You were listening over this side? 2, 3, 4 and 5 didn't even get a mention.
We did.
Ariana.
Yes.
This way. 10, 11, 12 didn't get a mention. Lots of 7s. What's going on? Something's not right. Or is it?
It's the 17th of the 7th.
It is the 17th of the 7th. Is it? Is that why?
It's actually,
Oh, there's a bit more to it than that.
it's kind of in the middle.
It's kind of in the middle. So it's got something to do with this diagram here. So what this diagram is just a table that allows us to combine the 2 events. So one side is one of the die, I've just called it white. The other side is blue, let's say. And the 6 numbers that come up on either die. And in the middle, what's this? What are these numbers? What's 2, 3, 4, 5? What's that representing?
What numbers you have to add?
Yeah, the sum. So adding those 2 numbers, 1 and 1 makes 2. This one, 3 and 2 makes 5, and so on. Finish the table. You've got 30 seconds. What's going on here? Have a look at this table, and Freya, you can't answer.
Why?
I want you to tell me what is significant about that table and how it links to our tally on the board. Julia, what is it?
It's like possible pairs.
Yes. Have a look at how many times we can make a sum of 7 with a 2 die roll. There are more ways to make sum of 7, 1, 2, 3, 4, 5, 6, than any other number. Followed by 6 and 8, followed by 9 and 5, and so on. Hence the reason why 2 and 12 don't even come close, unless you make a mistake. And similarly, 3 and 11, very, very unlikely. Not impossible, but very, very unlikely. And 7 is the front runner. So those of you that were guessing 7, I don't know if that was the reason or if it's because 7's your lucky number, but you did a good job guessing 7, because there are more combinations that make 7 when you sum 2 die. And so we would expect that 7 would come up the most. Now, if we go back to our little simulation, can I have people just stopping for a moment? If we were to reset this and roll the die 100 times, oh, that was quick. In 100 goes, actually this one had 6, 7 was second compared to... So this is what happens with experimental probability. Even though in theory we've just drawn a sample space, where it's got all the 7, all those extra 7s. In reality, it doesn't always work that way. And hence the reason why casinos make lots of money, because what happens in what you think in theory doesn't happen in practice as you would expect. However, in the long run, if we do this 1,000, 10,000 times, look at where 7 pops. Right, so eventually it starts to kind of even itself out. You can see 6 and 8, relatively out of 10,000 rolls of the die, relatively they're almost the same. Similarly with 5 and 9 and so forth. So this is a pretty cool little example. And if I add another 10,000, just to make it even more interesting, you can see there it evens itself out even more. Look how close 2 and 12 are, 560, 552. Now as a fraction over 20,000, they're almost the same if you change them to a decimal figure. So anyway, I thought you might find that interesting. Back to our sample space, which shows all the possible outcomes for a sum of 2 die on a 2 die roll. Answer the question, see how you go. With this first one, we get 6 out of 36 or 1 on 6. Now, logically, why is that not working? Logically, it should make sense that it is 1 out of 6, because there's one chance of getting a 2 in 6 on one die. Or there's 6 outcomes. Something's wrong with my Vivi. There's 6 outcomes in which the 2 on the blue die occurs. You've got your sum of 3, sum of 4, 5, 6, 7, 8. So there's 6 outcomes there. So if a sum of 4 is 3 on 36, what is not a sum of 4? You don't want to go counting all the ones that aren't a sum of 4. 33. Yeah, it's the complement. So remember, they add to 1. So 33 on 36. An even sum and an even number on the blue die. So here's your even numbers on the blue die, that one, and that one. But we also want an even sum. So out of all of those, which ones are even? 1, 2, 3, 4, 5, 6. Whoops, forgot the ones in the middle. 7, 8, 9. So 9 have an even blue number, and a total sum that's even. So there's 9 of them. Greater than 8, does it include 8?
No.
No. So greater than 8, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 36. A sum of 8 or less. What do you know about part 5 and 6? If it's not greater than 8, it's got to be 8 or less. Complementary events, again, so you don't need to go and count all of those. A sum that is not a factor of 4. What are the factors of 4? So if you've got a factor of 4, you're looking at what numbers? 1, 2 and 4. So any sum that is not 1, 2 and 4, so it's easier to go, well, there's 1, 2, 3, 4 factors, 4 of them that have a factor of 4, so 32 of them will not. And now the last one is a challenge. I don't think I've seen anyone get this right yet. So let's have a look at it. To win a game, if you must roll a 2 or a sum of 7. To win a game, you must roll a 2 or a sum of 7. That word if doesn't belong there. To win a game, you must roll a 2 or a sum of 7. So rolling a 2 or a sum of 7. Now I'm assuming that's not a sum of 2. That's just rolling a 2. So you can roll the 2 on the blue, you can roll the 2 on the white, and you can roll a sum of 7. Now, in maths, when we talk about or, we're talking about anything I've just showed it. It incorporates any of those options. A 2 on one of the die or a sum of 7, including both. So anything I've shaded in pink. So you've got 1, 2, 3, 4, 5, 6, 7, we don't count that one again. So it's 7, 8, 9, 10, 11, and then what's left? 13, don't count that again. 14, 15, 16. That's a bit tricky. People see that? It doesn't help when I've got numbers all over the place or shading all over the place. Let's get rid of all that shading. So the statement was, you must roll a 2 or a sum of 7. So the sums of 7 is this, and this. The 2 is, this is the blue that's got a 2. This is the white that's got a 2. So any cell that I've shaded, we don't double up. So hopefully that works to whatever number I said before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that what I said before? Oh gosh, did I miss? Well, I haven't missed, I must have miscounted before because I know I haven't missed one here, I don't think. So let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I overcounted one. So 15 out of 36. So anything that I've just said, or means any, but we don't count the same thing twice. So that's an important idea. You can see this 4 has a 2 on the blue and a 2 on the white, but we don't count it twice. We only count it once. And similarly with this, that 7 comes into play here and as your sum of 7. So that's two-stage events. How do we use the 2-die roll in a strategic game? Monopoly is one of them. So here we have a scenario. If you don't know Monopoly, hopefully people have seen Monopoly, but if you don't, it doesn't matter. If you haven't seen Monopoly, that's sad. That's really sad. But anyway, that's okay. So what you've got to do, you've got to find the street. So you own, those of you that have played will know, Regent, Oxford and Bond. So you own these ones, Regent, Oxford and Bond, and your opponent is on Waterworks here. You've got enough money just to buy one hotel, just to give them annoy them if they land on it. Forget about double numbers and all that business about if you roll a double then you roll again and you don't have to pay up. Just in general, the idea is where would you put the hotel? 1, 2, 3 away is Regent, 4 away is Oxford, 5, 6 away is Bond. So if it was one roll, if that was the last roll of the game, then you'd put it on Bond because you've got more chance of rolling a 6 than you have any of those other numbers. If it wasn't the last roll, you might think strategically, well, if she rolls a 3 and then another 3, you got a chance to get 3 twice and another chance to get 3 here. I don't know, you could think a bit more strategically like that. But if it was one roll, then you would go for Bond. Anyway, that was the idea behind that one. Okay, this time it's for you to draw a sample space. What would a sample space look like? We call it an array because it's kind of like a table that joins up. A normal die and a coin toss, what would it look like? Our prime numbers. What are our prime numbers? Very year 7, yes. What are our prime numbers? 2? 2 is the only even prime. 1 is not prime. Why not? Definition of a prime has got 2 factors. 1 has only 1 factor, so it's like a special number. It's not prime, it's nor it's a composite. So 2, 3 and 5, because they're the only numbers between 1 and 6 that have got 2 factors. Exactly 2 factors. So probability of getting a prime number on the die, well, you've got that one. No, oh gosh, that was wrong of me. This one, I mean, those two, and those 2. So you've got 2, 4, 6. 6 out of 12 or just a half. Now what I really want to focus on is the difference between and or. See if you can do that on your own without me telling you. How are those 2 different? Think about it, give me a probability figure. So and means both, essentially both at the same time. Tail and a 5, both tail and 5 at the same time. There's only one option there. Tail or 5 means, well, it could be tails, could be 5. You don't count any double ups though. So I've highlighted 1, 2, 3, 4, 5, 6, 7. So or includes both of them. One or the other or both. It encompasses any option, any possible option there. A tail or an even number on the die. Well, we've done a tail already. We don't want that one. Even number on the die. So you do need to understand the distinction between and or in a probability scenario. All right, let's finish off with revisiting the horse race. This time we'll do a difference. So you guys at the back there, you can use that first table that you had, I think, because that might work. I want you to think about the difference and think about what we've just learnt about sample space and how you might set up a sample space for the difference and predict which difference you think will be the most likely to come up. So I'll let you think about that. Think about, you might want to do a little sample space sketch to see what that might look like. Up to you. So using this sample space, 1 will come up the most, followed by 2. All right, we'll leave it there. Thanks, everyone.
Thank you.